All right, so now we're ready to talk about the epsilon differential privacy with Dirichlet-multinomial model. Again, Dirichlet-multinomial is a conjugate Bayesian model for counts, okay? And epsilon differential privacy is a form of privacy guarantee that now we're trying to marry these two together to produce what we call differentially private synthetic tabular data, okay? So let me cover the way to do it first and then show why that works, okay? So to generate a differentially private synthetic count vector, we are using Y star here, bold Y star. Given, so again, we are making sure that the total sum is fixed, okay? We're just rearranging, you can think of it as rearranging the counts in different categories, but then the sum wouldn't change, okay? So what we do is we first of all, so you can see that equation 6 is actually no different from the posterior that we showed you earlier, okay? So we first of all sample the parameters theta star from this, I wouldn't call it posterior, we will see why that is the case, but it looks very similar to what we saw before, okay? So you will have you can, yeah, let's just say this is the posterior for now, that we have the posterior of theta given y, right? It's y plus alpha, the two vector taking the sum, and then that goes into the Dirichlet distribution. But you can see that we have a requirement here that the one that is highlighted in red is what we have to make sure to satisfy in order to have a differentially private synthetic count vector, okay? And you can see how epsilon is playing its role here. We're saying that, yeah, first of all, you sample theta star from its posterior, but it's a very special posterior in a sense that we have to make sure that our prior satisfies this requirement. So the requirement is saying that the minimum of alpha I, so again, we have this index I because, well, alpha is a vector of length capital I because that's how many categories there are, okay? So we have the minimum, so this is saying that any of the alpha I out of the alpha vector should be at least the sum of the y's divided by the exponent of epsilon minus 1, okay? Might look a little bit confusing or not sure why that is the case. So like I said, we're gonna talk through maybe not too much in detail about why that is the case after we cover the procedure, but we highlight it here because that's the key. So as I was saying, equation 6, if you don't have this requirement of the minimum of alpha I needs to be at least this number, it's no different from before. It's no different from a regular non-differentially private synthesizer, right? Like this is just a typical Dirichlet multinomial if you want to do it. But now we are adding this requirement because this requirement is what satisfies the differential privacy definition. Okay, so keep that in mind. We're going to see why that is the case, but you can see now how epsilon, right, is affecting the prior choice of alpha. And then once we do that, the next step is very straightforward. You can think of that now my theta star, the parameters are differentially private, so the synthetic data generated from it will be differentially private. Okay, so that's what equation 7 is about. And as you can see that the procedure is really, we are doing something very similar as before. We're doing posterior predictive, right? Like 6 is the posterior and 7 is the posterior predictive. But in order to satisfy differential privacy, equation 6, the regular posterior distribution will have to satisfy this requirement about its prior, okay? So one thing I want to highlight, which is easy to get confused in this setting, is that y, okay, is the data. Y is, sorry about that, I have to redo this, okay. Y is the data, okay. Theta is the model parameter, okay, and alpha is the hyperparameter. Okay. Alpha parameter, yeah. I want to highlight this mostly because, well, I want you to notice what is what we are trying to satisfy here for. Theta is the parameter, right? Theta at the end of the day, because we're working with count, this will be a probability vector, add up to 1, okay? And but you can see that we are the first step sampling from its posterior, which is fine. Y is the data, right? Alpha is the prior. But you can see that DP, differential privacy, now requires the prior satisfy certain condition, okay? And we say this is because alpha is the hyperparameter which goes into the prior, okay? Remember, this is the original prior that you will have, okay? From the previous or a couple of slides before, okay? So this is the prior, okay? So what I want to highlight now is that, well, why it is what it is, that's what the data is, right? And to satisfy differential privacy, what we're really doing is to play with the prior. And we have to make sure that the prior satisfy this seemingly vague and not sure why condition here. But I want to highlight this to you that equation 6, sampling from the posterior, and the posterior is combination of the data and the prior, and you can see that the only change that we really want to make or need to make here is to satisfy the prior to some degree, okay? And this is the whatever the condition that we need to follow, okay? And then from equation 6 to equation 7, no big difference from before. When you have your posterior draws, right, theta star, you're going to generate your predicted values, which will be our synthetic data, and that again is from the sampling model. So as we say that this is the posterior, this is the posterior predictive. Okay. There are some really nice properties, which I will mention even more next week when we talk about differentially private microdata, synthetic microdata at the individual level, is that there is nice property to guarantee us that if you are able to generate differentially private parameters, like what we do in step 1, then whatever the synthetic data that you generate, like in step 2, from differentially private parameters will be differentially private, okay? So as you can see that now, we are really trying to make sure that the parameters that we generate from its posterior, they are differentially private. And that's why you see that the condition is being applied here about theta, okay? And then from theta to y, or from theta star to y star, because theta is now based on equation 6 and satisfying this condition is differentially private, then the y star that we generate from differentially private parameters will be differentially private. Okay, so that's a property. And so here, this is the general framework. And in practice, it's not complicated, as you can see that, well, we know what y is, right? We just need to make sure. So we know y. First of all, you get the y, it's a vector count from the original data, it's fixed, okay? And you take the sum of them to get this y dot star, because the sum doesn't change. If you decide how large your epsilon is, maybe 5, maybe 10, maybe 1, maybe 0.1, then you're able to compute the minimum of each alpha I. And then we use the same value for the entire vector of alpha, so you're able to do step 1 and step 2. Okay? So in practice, nothing complicated. But of course, you might be wondering why we have to satisfy this condition, okay? So again, I don't want to overwhelm you too much, but I just want to mention that what we're doing right now with the equations and all that is no big different from what we did before. And it's just a lot of derivations and math involved. But I want to give you the general picture here, okay? So on the left-hand side, this is what? This is the posterior predictive, right? This is the y star given the data and the prior, okay? And we always do this, as you know, that we can add back the parameters and then integrate it out, okay? So this is a typical technique, and I guess the most, probably the only time that we really did the derivation was very early on in the Bayesian course, that we're trying to show that y conjugate works. Like say y, the posterior of a parameter, if it starts with the beta prior and then combined with a binomial likelihood, we are coming to a final beta posterior, okay? So this is very similar to the derivation technique. What we're claiming here, as you can see, is that, well, if we have, so this is the posterior predictive, right? or I should say, let me take that back. This part, the one in the box here, this is the sampling model for the synthetic data, and this is the posterior, right? So the posterior is what? Is a Dirichlet. Okay, and the sampling model is what? Is a binomial. Sorry, is a multinomial. Okay. So what we're doing in the first line here is really just expressing the density of the multinomial in Dirichlet. Okay, and then finally we simplify it into the final line. Okay, so what we want to show you here is that some of this are fixed, right? This y star, we know y dot star is the total sum, it's fixed. And then this, of course, is the product of the factorial of each of the counts, okay? And that, again, comes from the multinomial density, okay? Nothing fancy, it's complicated, but nothing out of blue. It's just we have to put all of the terms together, okay? So you don't need to like remember what this equation 8 is, but what we're trying to do is we are expressing the posterior predictive distribution now with all of the little terms, because later you know that we have to bound what? We have to bound the log of p y star given y alpha, right? Over p y star given x and alpha. We want to bound this above by epsilon, right? So what we're doing is that we're expressing one of this given y, the vector. Then of course we can do the same for given x. And then we take the ratio, we cancel certain terms. I mean, those terms, as you can imagine, going to be canceled because it's the same y star. But then certain things cannot be canceled, right? Whenever you have those yi. So as you can see, these two terms will stay when we take the ratio, but we try to simplify it as much as we can in order to finally prove what alpha needs to satisfy, what kind of condition alpha needs to satisfy in order to satisfy what we call this differential private definition, okay? Make sense overall? There's a lot of math going on, I agree, but the general story, I think, is not that complicated, okay? So we take the log, like I said, take the ratio, take the log, and then you're left with this, okay? And you need to bound it above by epsilon, by the definition, okay? And keep in mind, x has Hamming distance 1 from y, and then the total sum is fixed, okay? So it is very symmetric, as you can see, what we have in this part, okay? So because we want to bound this above by epsilon, we should think about what is the maximum possible value for this and what is the minimum possible value for this. I should say without the absolute sign. So we're able to show what alpha needs to satisfy. All right, so like I said, because regardless of how long the vectors are, if you have x and y with Hamming distance 1, the difference will only appear in one pair, okay? And we're assuming that is xi and xi prime and yi and yi prime. Because again, when the two vectors are different by one record, we're sort of moving one record from one category to another. So it's only going to affect two pairs, or like a pair, I should say two pairs, xi prime and yi prime. So just so you know, we're talking about this is the x, okay? This is the y. That just says this two, okay? And this is xi, this is xi prime. So the prime is on the index, okay? So we're using I and I prime. This is yi, and this is yi prime, okay? So we're saying that the difference only appears between this pair, and we assume that xi is yi minus 1, and the xi prime is yi prime plus 1. So we're only moving one record, and then that will be the difference that we're gonna see. So with that in mind, we can further simplify what we have earlier, the ratio, into this, okay? So certain things about alpha I, of course, and then about alpha, and also about yi star, and yi and yi prime, and yi prime, okay? And what we need to also keep in mind is that the sum of the yeah, this is fine. Yeah, the sum of the two cells, these two cells, the one y star cell once we have it, it's the two cells here, the pair, yi prime, yi star, y here. The sum of these two should be bounded above by the total sum, because it cannot go above that. So this is, you can think of this as a condition that we're trying to satisfy when we try to figure out the lower bound and upper bound of this. Okay. All right. And lastly, we are able to show that this particular ratio is maximized when yi prime is 1, yi star is 0, and then, oops, sorry about that. This should be, sorry about this. It should be y star. I will correct that. Sorry about this. And what I want to show you here is the general flow that we're able to bound the lower and the upper of this ratio by this in equation 11. Okay, so you can see that it's particular the sum, right? It's the sum, and this sum again is the same as y dot because we never change the total sum. So you can see that it's bounded above by alpha I divided by the sum plus alpha I, bounded below by the reversed, right? The reciprocal of that. So this tells us that we should bound alpha I, the minimum of it, by what we showed earlier. Okay, so this again is the goal. We want to bound this above by epsilon. Okay, and we have shown you that just from the previous slide that it is bounded below by the ratio of alpha and alpha I and alpha I plus y star, y dot star, and then bounded above by alpha I prime plus y star, y dot star divided by alpha I star. So we are able to show that in the end, the minimum of alpha I needs to satisfy this requirement. And that's what the highlighted red I showed you earlier. Okay. So again, the general procedure of proving this, as you can see, is that we follow this definition, okay? And we express what this in the context of what we're doing. And then we try to find bounds for alpha, okay? So for example, in the lecture, we won't have the time to show you another, like say, how about what if I want to do a beta binomial type of differentially private model? What you do is you follow the general procedure, right? This is always true. This is the definition that we're working with right now. So you will have to figure out how you can express this too, right? In terms of the beta binomial model, and then see what are the bounds that you need for alpha. Okay. So in the lecture, we show you the demonstration of how to do it for a Dirichlet-multinomial, and then you finally come to equation 13 as your result. But this general approach is very applicable to other conjugate model if you're working with count. Okay, so in the future, if you're ever interested in trying that, feel free. I hope that I sort of build up a foundation for you if you ever want to revisit any kind of methodology that we're talking about here.